Okay, continuing on, we're going to talk about isotope masses and being able to use the average mass for calculating the mass of a certain number of atoms. So as we move down here to section 2 on this page, most elements, like carbon and nitrogen and so forth, have more than one naturally occurring isotope. They have more than one isotope that will occur in nature. So for example, uranium has a 238 isotope. There's also a 235 isotope of uranium. So it's the average of the masses of all the isotopes that naturally occur. That's the average mass of an atom, right? And it is called its average atomic mass. And very often we don't say the word average, we just abbreviate it atomic mass. But we should keep in mind that this is an average of isotope masses. Now this average atomic mass does definitely appear on the periodic table. And that's what these numbers down here are. They're the average mass of that atom, because the atom is made up of different masses, because it is made up of different isotopes. Each isotope has a different number of neutrons in it, so we take the average. Generally, this number is far more important to us than the mass number, because we are generally in chemistry working with many atoms of, for example, carbon at a time. If you're dealing with a gram of carbon, you are dealing with an unfathomably large number of carbon atoms, and in that large sample of carbon atoms, in 1 gram, you will have carbon atoms that are carbon 12s, carbon 13s, and carbon 14s, each of which have different masses, and so we take the average of their masses. Okay, so this average atomic mass does appear on the periodic table. And because these masses are so small, we don't usually refer to them in terms of grams. We use a special, very small unit of mass to describe the mass of individual atoms, called the atomic mass unit. And this is abbreviated a.m.u. The a.m.u, the atomic mass unit, is a very small unit of mass. You can think of it like a gram or a kilogram. It's just extremely tiny. And the mass of the a.m.u has been defined. So the mass of the a.m.u is equal to be 1/12 of the mass of a single atom of carbon-12 isotope. So whatever the mass of a single carbon-12 atom is, they have defined it to be 1/12 of that mass is the mass of the a.m.u. So you can see it's a teeny tiny amount of mass. Whatever the mass of a single carbon atom is, it's 1/12 of that for a carbon-12 isotope. This allows us to calculate the mass of a certain number of atoms. And from now on, we're basically going to be talking about calculating, when we talk about calculating the mass of atoms or the mass of a compound, we're going to be talking about the average atomic mass. So we're now going to use this average atomic mass value that we find on the periodic table. And that's going to allow us to calculate the mass of multiples of atoms, and we will extend that into grams later as well. So we have a sample problem A, and this sample problem, fairly straightforward. What is the mass of 17 atoms of iron in a.m.u? Well, let's just go back to our periodic table. Remember this, there's iron, Fe, for iron, and this number is the average mass of a single iron atom. It's the average. What are the units of measurement? These are in a.m.u's, a.m.u, when we're talking about a single atom. So the average mass of a single atom of iron has a mass of 55.845 a.m.u. Okay? So we've got a conversion basically that we're going to be performing right here. So let's set it up. 17 atoms of iron. 17 atoms of iron. That's what we're given. And I want my answer over here to be a.m.u. So set up that way, I'll tell you that you can do this as a one-step conversion using a dimensional analysis setup. So I'd like for you to do that. Pause the video, do that math problem, and get the answer. Now, when you do this, you're going to get an answer, and you have to think about your sig figs, your significant figures. Because we are dealing with individual atoms here, let us, for the sake of this problem, assume that you counted out these individual atoms. If you counted out these individual 17 atoms, what does that mean about that number 17? How many sig figs are in that number? Well, remember, one of the ways that we can get an exact number is either by defining the number, like 60 seconds in 1 minute, or by counting individual objects. So if we're assuming that we counted these individual atoms, then that 17 becomes an exact number, and it does not limit my precision in my calculation. So where is the limitation of my precision going to come from? It's going to come from the average atomic mass right there. So you'll have to think about that when you figure out your sig figs at the end. So go ahead and pause the video now and do the problem and come back and we'll finish it up. All right, I'm assuming that you've done this problem. Let's go ahead and plug in some numbers and wrap it up here. I'm being asked for the mass of 17 of these atoms. So I put that on the far left of my dimensional analysis. And the answer should be in a.m.u, atomic mass units of mass. And so I put that on the far right. So I need a conversion factor that will convert from an atom of iron to a.m.u, right? So the way that I do my dimensional analysis is I always put in my units before I put in my numbers. I want to make sure that my units are in the right place so that I can confirm that yes, indeed, they do cancel to give me the units that I want in my answer. Now that I've done with that, the next step is to actually plug in the numbers. So the average a.m.u of mass for a single atom of iron is 55.845 a.m.u. So 55.845 a.m.u for every one atom of iron. And you can see now that I have all my numbers, there's nothing in the denominator, they're all ones in the denominator. So my answer is just multiplying the numerators across. So if I multiply 17 times 55.845, I get an answer that is 949 point, my calculator says 365. So before we move on, I have to think about my significant figures. If I have assumed that I have counted these 17 atoms as discrete individual objects, that is an exact number. It does not limit me. In multiplication, I'm limited by the fewest number of significant digits. That's exact though, so it's considered to have an infinite number of significant digits. So the one that limits me, the number that limits me is this 55.845. There are 5 sig figs in that number. So my answer should have 1, 2, 3, 4, 5 sig figs. So that 2 places past the decimal will be the last digit that I can represent. The 3rd place past the decimal is a 5, so we'll round that 6 up to a 7. So 949.37 a.m.u. Okay, and there we go, and I circle it. So again, I'm being nice to whoever has to read this so they don't have to go fishing around to try to find where my answer is. So that's how we calculate the mass for a relatively small number of individually accountable atoms of an element. Now you might say, is it realistic to count 17 atoms of iron? Not generally. As chemists, we don't generally handle, a dozen atoms of something or a couple hundred atoms of something. However, it is possible to count them with new microscope technology. Scanning, tunneling electron microscopes can actually see individual atoms, particularly larger ones, so they could be counted. But it's not realistic from a chemical standpoint to be calculating masses of just a few atoms of an element like this. Why did we do this problem, though? I wanted you to reflect on the fact that there is a conversion factor here. Every atom has an average mass, and its mass is given in a.m.u. Okay? All right, let's move on. All right, so we're going to expand on that idea of having an average mass for a single atom to now being able to do mass calculations on a very large number of atoms. And that's often what chemists tend to deal with. We deal with amounts of substances that we can actually see and interact with on the macroscopic scale, an amount of a chemical substance that you can pour into a flask or weigh on a balance or something like that. And once you get to the amount of chemical substance that you can actually see, then you're talking about an extraordinary number of atoms that are included in that sample at that point. Well, because we often measure properties of a very large number of atoms, we have agreed to use a very large number to do so, to express these large numbers. And the number, which I'm hoping that this is a review for you, the number that we'll use most often is called Avogadro's number. Avogadro's number. A-V-O-G-A-D-R-O. Avogadro, Amadeo Avogadro. Avogadro's number, which is the number specifically 6.022 times 10 raised to the 23rd, which is an enormous number, right? It's 6.022 times a number that has a 1 with 23 zeros after it, so it's just a fantastically large number. It's a number, frankly, that is too large for us to imagine, really. Our minds have a difficulty wrapping around a number that is that large. But we're going to use that number a fair bit. It's called Avogadro's number. You may have learned in earlier chemistry that it's just 6.02 times 10 to the 23rd. But in this class, we're going to expand it a little bit so that we have 4 sig figs in that number, so that doesn't limit our precision as much. So what is Avogadro's number? It is that number. And it is defined as the number of carbon-12 isotope atoms in exactly 12 grams of carbon-12 isotope atoms. So if you have a sample that you were able to get exactly 12 grams and only of carbon-12 isotope carbon atoms, then you would have that many atoms in that sample. Another word that we use to describe this many of an atom is called a mole, M-O-L-E, a mole. So I just want to take a moment here to say this word, the mole, that is just a word that we have for a number. For example, we have the word 100 to describe this number. We have the word 1,000 to describe that number. We have the word dozen to describe that number, and so forth. So the word mole describes this number. So it's just a word for that number, okay? So this next problem, example problem A, I want to use this problem just to kind of calibrate your thinking about just how enormously large this number is. So we're going to relate that number, the mole of something, an Avogadro's number of something, to the number of grains of sand in all of the world's beaches. Now you can imagine that if you had to count every grain of sand in a bucket of sand, oh my gosh, how long would that take you? It would take you years, possibly. Now imagine that you had to count all of the grains of sand on a whole beach front full of sand. So we're talking about an unfathomably, incomprehensibly large number, right? So someone on the internet, well, if you know someone on the internet did it, you know it had to be right, right? Because everything on the internet is accurate. No, that's not true at all. The internet is full of things that we have to be careful about reviewing, and just because we read something on the internet does not mean it's true. But this person roughly estimated the number of grains of sand in all of the world's beaches all over the world as being about 5.6 times 10 to the 21 grains of sand. I'd like to point out right away that this number is smaller than Avogadro's number. So, based on this rough estimate, there aren't even an Avogadro's number. There aren't even a mole of sand grains on all of the beaches in the world. So that's how unfathomably large a number we're talking about here. Well, we could calculate, if we accepted this value as being accurate, I'm not sure it is accurate, but for the purposes of this problem, let's go with it. If we accepted that number as how many sand grains are in all of the world's beaches, how many moles of sand grains are there if this estimate is accurate? So we could say we're given 5.6 times 10 to the 21, 5.6 times 10 to the 21 grains of sand. And we're asked for the moles of grains of sand, right? So I'm going to convert from these grains to moles. And remember, a mole is just something, a number of something. So how many grains of sand are in a mole of sand grains? Well, I've got my grains canceling out. I've got my moles up top where they belong. If I have 1 mole, I have an Avogadro's number of grains in that mole, right? So now I can do my math. I can take this number divided by that number. And I'm going to show you how I plug this in on my calculator, because some of you do have this type of calculator with the double E function. This is the TI-30X, or 30XA in this case. Some of your calculators will require you to plug this in differently. You will have an exponent, an EXP button. Some of you will have to do it slightly differently. So 5.6 times 10 to the 21. So on this calculator, 5.6, and then I hit the EE button for exponent, and then 21. So there's 5.6 times 10 to the 21. Then I hit times, well, that's times 1 equals, right? So that just gives me my numerator. Then I have to divide it by this number, this Avogadro's number. So divided by 6.022 times 10 to the 23rd. So divided by 6.022 EE for the exponent, 23rd, okay? And there's my number. And look how small it is. It's not even 1 mole. Well, we knew that by looking at the problem. That's not a mole. 0.009. How many sig figs do we need in here? Well, it's a pretty good bet that this number was not counted specifically. That's too large of a number intuitively for us to think that somebody counted that many sand grains. So this is an estimate, okay? So there are 2 sig figs there, 4 sig figs there, so our answer should have 2 sig figs in it. 0.009 will be our first sig fig, and that 2 will be our next sig fig, but it's rounded up to a 3. So it's 0.0093. So that's standard notation. I could easily represent it in scientific notation as 9.3 times 10 to the minus 3. So either of those numbers is acceptable. There's the standard notation, there's the scientific notation. Both of them have 2 sig figs. And whichever one you want to be your answer, circle that, and you're done with it. So look at what we have. This is, again, just to give us practice working with the Avogadro's number in a dimensional analysis. It's also to help us begin to internalize just what an enormously large number Avogadro's number is. If you were to take all of the grains of sand in all of the world's beaches, you would get about 0.009, so about 1/100th or 9/1000ths of a mole of grains of sand. Well, we're generally not going to use the word mole or the concept of the Avogadro's number for species other than chemical particles like molecules or atoms or electrons or things like that. So let's take this second example, and we're going to apply the same principles to it. So example B says how many gold atoms are in 2.3 moles of gold. So basically you'll start with 2.3 moles of gold and you'll convert it to atoms. And how many atoms are in a mole? Well, it's that many atoms are in 1 mole. So that will be a one-step conversion. Then for example C, this gets to be a little bit more challenging because now we have to figure out how many hydrogen atoms are in that many moles of a compound. And you'll notice there's not just one hydrogen in that compound formula. There are 3 hydrogens. So I'd like for you to try those two, see if you can do those. You might struggle a little bit, especially on example C, but give them a shot, see if you can do them. Pause the video and then resume when you are done, and we'll go through it together. Okay, let's work through these now. The example B is a fairly straightforward problem. It's a one-step conversion. We're going to start with 2.3 moles of gold. And we're speaking about gold atoms here, right? And we want the number of gold, or a.u, I guess I should have written to be consistent, atoms. Well, it's a one-step conversion. We're going from moles to atoms. And we know that for every 1 mole, we have 6.022 times 10 to the 23rd atoms. Again, we're going to use our chemical intuition and assume that that is an estimated number. Someone didn't go out and count out 2.3 moles of gold atoms. So there's 2 sig figs, 4 sig figs. Our answer will have 2 sig figs in it. So I multiply the 2 numbers across the top. All the numbers on the bottom in the denominators are 1s. And my answer, rounded to 2 sig figs, is 1.4 times 10 to the 24. Does that make sense? Well, it should. 1 mole of atoms has that many atoms in it. And I have 2.3 moles, so it should be a larger number than that many atoms, and that's what I've got. Now, example 3 may have given you a little bit more of a challenge, so let's take a look at that one. How many hydrogen atoms are in 1.3 moles of that whole formula? So let's start with 1.3 moles of that whole formula, 1.35 moles of that whole formula. 1.35 moles, H3PO4, aqueous. That's actually the formula for phosphoric acid. And over here I want to have my answer in hydrogen atoms. Well, notice that my substances are not the same here. In the previous example, I started with moles of gold and I ended up with gold, right? So it's the same substance. But now my dimensional analysis does not have the same substance, okay? So I'm going to have to first convert the number of moles of this compound formula into the number of these compounds. So let's do that. So moles of H3PO4. And the term that we use to describe the number of these individual compounds is the formula unit. So we're basically saying how many units of this formula, of the formula unit, Fu, of the how many formula units of this do I have in a mole of those formula units? Well, for every one, you know I'm going to have an Avogadro's number, right? So let's do that. We'll finish up our dimensional analysis, then we'll come back to it. And maybe it'll cancel out the number of moles of that formula unit. And now I just have the number of formula units of that H3PO4, right? Well, now I want to convert from the number of formula units of H3PO4 to just the hydrogen atoms. So every formula unit of H3PO4 has how many hydrogen atoms in it? Well, for every unit of this formula, you can see I have 3 hydrogens. So 3 H atoms, right? So the number of formula units of phosphoric acid cancel out, and I'm left with the number of hydrogen atoms. So let's plug in the numbers. How many formula units do I have in a mole of a compound? Well, in 1 mole of the compound, I have an Avogadro's number of those formula units. And in 1 formula unit of that compound, I have 3 hydrogen atoms. So I want you to take a moment and look at what I did. I converted from a compound, the number of moles of a compound, to the number of individual units of that compound. And then I converted from the individual units of that compound to the number of hydrogen atoms in each of those units. So I want to make sure that you're tracking why I'm doing the math that I'm doing. All of the denominators are ones, so I don't need to worry about the denominators, so it's basically multiplying the numbers across the top. So let me do that. 1.35 times 6.022 to the 23rd equals, and then multiplied by 3 equals. And my answer should be rounded to 3 sig figs, 1, 2, 3, 4 sig figs. This number is exact because I have exactly 3 hydrogens in every formula unit of phosphoric acid. 3 sig figs, 4 sig figs. I need my answer in 3 sig figs, so I'm going to round my answer to 3 sig figs, and it is 2.44 times 10 to the 24th hydrogen atoms. So for every formula unit of phosphoric acid, I have 3 hydrogen atoms. But I have 1.35 moles of these. So I basically have to say I have 1.35 moles of those formula units. How many individual formula units do I have of phosphoric acid? Multiplied by 3 hydrogen atoms per formula unit. And that's how I get my answer.